Hello and welcome back. My name is Mike Price. Today we are talking about section 1.4, functional models. In particular, we're going to jump into the second learning objective, explore a variety of applied models, and in particular, we're going to be talking about proportionality. So when we talk about proportionality, basically, this is one of those mathematical modeling strategies that comes up a lot in applications. So business economics, some biology, human physiology applications involve proportionality. So it's a worthwhile thing to study. It does involve a little bit of terminology. The pieces that we're going to talk about are, so if we have some quantity, we can talk about this quantity being directly proportional to something else. Sometimes, in fact, maybe even frequently, if it's just written proportional to, then the assumption is we mean directly proportional. So we say that z is proportional to x if this equation completely describes their relationship for some constant k. Yeah, sort of the Kraft mac and cheese of constants. We'll spell constant with a k. But really, what this means is that another version of this equation is that if we divided both sides by x, so z over x, all that would be left on that right side is k. So in other words, if you take the ratio of these two numbers, z divided by x, and you always get this constant, then what you have is these variables are proportional to one another. You might also notice that this is kind of a special line. It's just a line with slope k and y-intercept equal to 0 because there's nothing over here. It's plus 0 is the assumption. So we don't have to be directly proportional. We could be inversely proportional. So if z is inversely proportional to x, the only change is that instead of taking k and multiplying by x, we take k and divide by x. So there's that inverse kind of notion. And then it'll come up less for us when we're only talking about functions of one variable, but we could also talk about a variable being jointly proportional to two things, in this case x and y, just for our simple definition. So in that event, we'd have k times x and times y. And what might occur for us is we will see jointly proportional variables in the event when we could write y in terms of something to do with x. So we could write this as k times x times some other x stuff. And then k gets a special name. It's the constant of proportionality involved in these. So again, there's nothing special about k. It's just the letter we've used here, but it turns out that for whatever reason, a lot of the time, we will use k along with c to represent constants. So we'll try this in a business example. So the claim is that the piece of average cost associated with maintenance is inversely proportional to how many units you sell. And then the piece of cost that's associated with sales is proportional to the number of units sold. So again, since the word directly is missing here, we're going to assume that that's what it means, that this cost is directly proportional to the number of units sold. And then our entire task is to write an equation for the average cost as a function of the number of units sold. So just breaking this down, write an equation, so it's going to have some equal sign, something in there. The average cost as a function of number of units sold. So average cost is going to be our output, and number of units sold is going to be our input. That's what blank as a function of blank means. Well, we've got two pieces basically to consider. Average costs, they are telling us, is made up of maintenance and sales costs, respectively. So the first thing we'll tackle is the maintenance portion of this, and we're told just back in that original statement there that it's inversely proportional to number of units sold. So just using our definition of inversely proportional, we can take average cost of maintenance, and this is a very long name of a variable, but AC, average cost, and then it gets the subscript just because there's going to be another portion of this. We've got maintenance costs, but we've also got sales costs. So we're just thinking about the piece that's maintenance. That's k over x. And again, we're just specifying, doing due diligence and saying that this k thing that appears here is some constant, because otherwise we'd have no idea what this is. X is number of units sold, AC is average cost, k is something fixed. So then the other half of this, the sales piece of average cost, we are told is proportional, directly proportional to number of units sold. So now we can write the portion of sales, the portion of average cost that's due to sales as ACE with a little subscript sales. And we're using a different letter here because I'm not totally sure that the K we used before is the same constant of proportionality we should care about right now. So we pick something different. C is a good constant, I don't know, by somebody's idea of what good means. And directly proportional just means it looks like average cost equals that constant times X, the number of units we sell. And then we put it all together. Average cost is, notice there's no subscripts here. This is the full-on real deal average cost. That's made up of these two things. And way back in the beginning, they told us that it was the sum of average cost due to maintenance and average cost due to sales. Sum just means take these two things and add them together. Average cost for maintenance was K over X we had. And average cost due to sales was from this thing we just put together, directly proportional. So add those two things together, you get average cost. What would make this yet more exciting, but also probably more valuable, is if we had a couple of data points telling us when we sold this many units, what was our average cost? Because then we could actually nail down what these constants are. If we had a couple of data points, we could figure out a number for K and a number for C, and then we'd have an average cost function that would actually allow us to compute for some new number of items how much average cost actually is. Okay, that's it for Learning Objective 2 from section 1.4. We'll be back with our final learning objective in the next video.